too much stuff up here. We don't need that. Come on. All right. All right, sorry about that. I was looking for a page in my notes and it just slightly misplaced, so it held me up. All right, so as a reminder, test 2 is on the horizon pretty soon. It is going to cover these 1, 2, 3, 4, 5, 6 sections worth of material. We said that we'll come back and fill in some gaps if we have time at the end of the semester, but we're just making the best of what we can, blah, 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 blah. I still have that as an open date for now. It's going to be 1 week after finishing 3.6, and then you'll have your 2-day period to complete it. So I highly doubt that we're going to be able to finish 3.6 today. We might not. So if we finish it today, then that means I'd be able to throw the test on July 2nd. Or if we finish it next class, then the test would start on July 7th. So again, just let's hold on to that. Let's see where we end. If we finish 3.6, I'll come back and give our firm test dates for now. Your homework due dates are as follows. We will definitely finish 3.4 today, so that's due in a week. That's the 2nd, isn't it? I don't know why we're at the 3rd. 7-2. So 3.1 and 3.2 we're due on the 30th, this Tuesday coming up. 3.4 is due on July 2nd. 3.6, maybe July 2nd as well, maybe not, we'll see. But let's continue where we left off in 3.4, optimization. So, quick recap. We said that when we talk about finding absolute extrema, we're not just taking our nose to the board or the piece of paper or whatever we're looking at and only looking at the area just around it. We're no longer doing that. We're looking at the whole picture, or at least the picture that they tell us to quite often, and for us pretty much always. We're looking on bounded intervals. Now in the real world, sometimes you have to come up with the bounded interval for the problem. Like if you're talking about producing some number of units, it wouldn't make sense to produce less than 0, so we could say 0 is the smallest. And then maybe your factory is only capable of making 1,000 units, or maybe the predictive model for your revenue falls apart after 1,000 units, something like that, so that would be your maximum range. So absolute extrema is just the highest high or the lowest low. That's all it is. It's not, you can't have multiple minimas and you can't have multiple maximas. It's just one of each. And there's in general one of each. If you're not looking at a bounded region, then there could be one missing. There could be just a max and no min, or vice versa. Or there could be neither. But that's not the type of problem I throw at you in this course. So what do we do? Well, you still need to find the first derivative of your function so you can then find your critical numbers, but you're no longer going to do the first or second derivative test. You're just going to take your critical numbers, plug them into the function, see what their outputs are. But you also plug the boundaries in, and you see which one's the highest and which one's the lowest, and boom, you're done. I've mentioned that you certainly can use the first and second derivative test for your critical numbers for just more evidence, but it's really unnecessary, and it also can't be used for the boundaries. Remember, you can only talk about local extrema using first and second derivative tests. For absolute extremas, it's an unnecessary test. And we did a couple examples. Go back to last lecture's notes if you need more information. And let's pick up where we left off. This should be, going to do another profit problem. Our example 3. It's going to be a word problem. Yes, example 3. It costs the American Automobile Company $8,000 to produce each automobile. It has fixed costs like rent, etc. are $20,000 per week. Company's price is P of X. Make sure I got enough space here to work later. Equals 22,000 minus 70x. P, price at which exactly X cars. They are sold. There we go. Question A. How many cars should be produced each week to maximize profit? Question B. What price should they be sold? Question C. Why did it do that and then that? Oh, technology, doesn't matter. What is the company's maximum profit? I tell you, I love problems like this. I really do. I love them, love them, love them, because of how relative they are to a lot of people. A lot of people are in business, and a lot of people want to make money, and you make money by maximizing profit. Not only are you interested in how many units you should make and what price they should be sold, but you also want to know how much money are you making. Okay, so we're gonna, oops, didn't mean to do that. That was more weirdness. First of all, it is well known, I hope it's well known, that revenue is price times quantity. Money in is the price you sell it for times the number of things you sell. If I have apples that I'm selling at $2 each, if I sell 5 apples, I make $10 in revenue, 5 times 2. In other words, R is equal to P times X. P times X, that's P times X. If you need to be super emphatic, you can put a little multiplication there. That is a multiplication. Well, we have the price function. They gave us P, 22,000 minus 70x. We don't know the X, it's a function. So the revenue should just be this thing times that thing. So your R of X, this is your revenue. It's price times quantity where this is price. So it's 22,000 minus 70x times X. Can I write it this way? Whoa. Brought my volume down some again. It was fine earlier. Can't do it this way. That's not a proper product because you got a binomial. So you got to make sure you wrap that in parentheses. And of course, you can distribute the X and you get 22,000 X minus 70X squared. Revenue functions tend to be quadratic or higher if they're polynomials, and often they're rationals or radicals like square roots or fractions. So this is kind of a simple revenue function. The true real life ones, if you want to go over extended periods, tend to be exponential or rational or radical, but we're keeping simple models, so we go polynomial. So there's our revenue. All right, well, the question was how many cars should be produced each week to maximize profit? Our ultimate goal is to talk about profit. Profit is the difference of revenue and cost. I don't see anything about cost though. So there's our revenue. Let's get to cost now. What? Cost. This should be cost per car times the number of cars plus any fixed costs. This is the traditional fixed variable amount plus fixed amount model. This is the standard linear cost model. You have your fixed costs and you have your variable costs. Variable costs tend to be the price per item to make on your end times the number of them that you're going to make, and then you add in your fixed costs like your rent. So they told us that it cost this automobile company $8,000 to make each vehicle. So if they make one car, it's going to cost them $8,000. If they make two cars, it's going to cost them $16,000. If they make three cars, it's going to cost them $24,000. It's just the 8,000 times the number of cars. That's the variable cost of this model. That's what we're talking about here. The cost per car times the number of cars. That's the variable cost. Then you add in your rent, which is not based on the input, your rent being the $20,000 a week. So your cost function would be the $8,000 per car times the number of cars. We've said X is the number of cars. X is the number of cars sold. So this is the variable cost, plus then we have our fixed cost, which was the rent, the $20,000 a week. So this is all in weeks. So if this company makes 0 cars in a week, they're going to pay $20,000 in rent. If they make 1 car, they're going to pay the $20,000 in rent plus the 8,000 to make that 1 car, which is $28,000. Now, if they sold that car for $20,000, if they only make 1, they're going to lose money because all they're going to be able to do is cover their rent and not that first car they made. But if they made 2 cars, that's $16,000 to make the cars, $20,000 in rent, that'd be $36,000 total. If they sold it for $20,000, they'd have $4,000 in profit. Because 2 times 20 is 40 minus the 36. If they make a lot of cars, they'd make a lot more. Now, again, I was just spitballing some revenue numbers. We actually have a guided revenue function. So we have our cost function. We have our revenue function. That means we can find our profit function. As a reminder, profit is the difference of revenue and cost. Money in minus money out. So P of X. Let's do this in, I don't know, purple, I guess. This is the revenue minus the cost. The revenue minus the cost. It's the red minus the green. All right, so now just doing everything in purple, that's the 22,000 X minus the 70 X squared. That was this. Then we go minus the cost function. Now the cost is multiple terms, so guess what? You need a parentheses. Then our 8,000 X plus 20,000. Revenue minus cost. You have to know that in this course. So therefore our profit function, I think I changed purples. That's okay, I hope. We can distribute the negative, so we get 22,000 X minus 70 X squared minus 8,000 X minus 20,000. So our profit is, let's actually get these in descending order. So the minus 70X squared, that goes first, we're done with that one. Then we have the 22,000 minus the 8,000X, which is a plus 14,000X. Where'd the 14 come from? 22 minus 8. And then the minus 20,000 at the end. This is our profit function. This is what we want to optimize. How do we optimize something? We take its derivative, we set it equal to 0 to find the critical numbers, etc., etc. So P prime of X. Bring the 2 down and multiply it by the 70, the negative 70 to get a 140, negative 140x. The 14,000x, taking that derivative is just a plus 14,000. Taking the derivative of negative 20 grand is 0. We set this equal to 0 to find the critical numbers. So we go 0 equals negative 140x plus the 14,000. You could add 140x or subtract 14,000, doesn't matter. I'm going to add the 140x. I just like to go ahead and get that positive first when I can. So that equals the 14 grand. It's not wrong to have done it the other way. Divide both sides by 140. If you did it the other way, you'd be dividing by a negative 140. Ultimately getting that x, scroll please, is equal to, well, the zeros cancel and 14 divided by 14 is 1, so that's 100. So there's only one critical number. This is our critical number. Now, there's something interesting about this problem. I said that in general, when we're dealing with these optimization problems, you're given bounds. This A to B, 0 to 2 million or something like that. This one had bounds, 0 to 3. This one had bounds, negative 4 to 1. I didn't give bounds. What are the bounds? Well, 0 must be the left bound. Why? Because why would you make less than 0 cars? You literally can't make a negative number of cars. The smallest number of cars you can make is 0. Remember, x is the cars. You can't make negative cars, so 0 has to be the left bound. So we're going 0 up to something. So the question is, how do you find the upper bound? And what I'm going to suggest that you do is you go to a picture. You go to the graph. Now, you don't necessarily have to graph this. There is a way to do it without the graph. And it's based on the profit function. If you set this equal to 0 and solve it via the quadratic formula, then you can find your upper bound, but that's just not going to be the most easy thing to do for us. So let's pull out our calculator. Let's go to the graph. And we're going to get the graph of negative 70 x squared plus 14,000x minus 20 grand. Now, this is a quadratic function. The profit is quadratic and its leading term is negative. So this is what I expect the graph to end up looking like. Because the graph is, again, quadratic, because the function's quadratic and it's got a negative leading coefficient, this graph is going to look something like this. It has to look like this. Oops, I erased the wrong part. That was weird. It has to look like this, which means that somewhere there has to be an absolute max. We know we don't want to have a negative profit, so we should probably stop at where the profit is negative. That's going to be my suggestion on where to do the upper bound. So we got our graph. If we just go to graph, this is going to look terrible because we see numbers like 140 and 14,000 and whatnot, or 22,000, excuse me. And No, 70x squared, 14,000, and 20,000. Those are really big numbers, so we probably need to zoom out a lot on this thing. A lot, a lot, a lot. So let's just zoom out. That still looks pretty bad. Maybe not just zooming out. Maybe just go to the window. Let's make the x minimum 0. We know we can't go past 0. X maximum, let's start with 20. And let's just make the y numbers. The biggest number I saw up there, the linear value, that is to say, was the 20,000. Maybe let's just double that and start with 40,000. So let's go from negative 40. Well, we don't even want a 0 profit, so let's make that like a negative 1,000. And let's make the y maximum, I'm just guessing, 100,000. Maybe that's too big, maybe that's too small. I know I said 40 originally. All right, so now this looks like a line. We know it should look like a parabola, so we're still not zoomed out enough. We're not high enough, and we're not far enough right. So let's make the x maximum, I don't know, 50. And let's make that y maximum 1 million. Maybe that's too far, maybe it's not. All right, we're still growing at oh geez, what was that number I put it at 50? So let's maybe take this to 200. There we go. There we go. Now I can see the peak of this graph, and I can see that eventually the profit goes to negative. And I can just trace over here. I type 400. I type 400, not 40. What was the Windows maximum at? 200, excuse me. I don't know why I thought I had 400. Let's try 190. We still have a positive profit. Let's try 200. We're at negative 200, sorry, negative 20,000. So if I actually go to calculate and find a 0, I can go to the left. I want to make sure the y value is positive, and there it's positive. And then I can go until I see the y value is negative. There it's negative. You can hit enter for the guess. And it says it's like 198 and some change. Well, I mean, that gives you a y value of 0. That's what that says. 1 times 10 to the negative 7 is roughly 0. So 198 and a half is about the maximum. So let's say it's 199. Okay. Now all we got to do is plug these in to the original function and see which one spits out the biggest number. So P, which the original function I did was in purple. So let's do the window of 0 to 199. We'll do P of 0, which that would be negative 70 times 0 squared plus 14,000 times 0 minus 20 grand. So when you plug in 0, you get negative 20,000. If you don't make any units, you're paying rent. That's what that says. So that's definitely not it. We don't want negative profit. How about P of 100 cars? If we make 100 cars, which we found to be a local extrema, that would be negative 70 times 100 squared plus 14 grand times 100 minus 20 grand. 100 squared is 10,000, just double the zeros, then multiply by negative 70, so that's negative 7, 0, and then 4 more, 1, 2, 3, 4. That's negative 700,000 plus tack on 2 more zeros to that, it's 1.4 million. 1, 2, 3, 4, 5, right? I did say that right, yes I did. Minus the 20 grand. $1.4 million minus $700,000 is going to be positive 700,000. Minus another 20,000 is 680,000. So at 100 cars made per week, profit is $680,000. You can even see that in the calculator if you don't want to do the work. Just trace and type in 100. Enter. Boom, 680,000. Now, I think it's very obvious looking at the picture, that's the highest profit. No matter what you plug in as a right bound, it just keeps going lower and lower and lower and lower and lower. Whether you plug in the 200 or the 199 that I said, and the 199 is really supposed to be 198 and some change, but you get the idea. They're going to be really close. And when you do this, you're going to get let's just type it in. Skip the work this time. Negative 6,070. Something you definitely don't want. You don't want to pay net. You don't want a profit of negative $20,000. You don't want a profit of negative $6,000. You want a profit of $680,000. This is the highest. So therefore, that's the maximum profit. So the answer to A, how many cars should be produced each week to maximize profit? 100 cars. For what price should they be sold? We have not figured that out, but we have figured out what the maximum profit is. We figured out A and C, but not B. We didn't do them in order, but that's okay. So part A was 100 cars. Part C was a profit of $680,000. And these are both as a per week. Part B, which they said was what price should they what price should they be sold for? Well, we use our price function. Our price was the thing they gave us, this 22,000 minus 70x. So we do P of 100 because we're going to make 100 cars. So that's the 22,000. Erase that. Minus the 70 times 100, which is 22,000 minus 7,000, which is 15,000. So this company produce 100 cars each week, a price of $15,000 to get a profit of $680,000, again, each week. If they produce 99 cars, their profit will be smaller. If they produce 101 cars, their profit will be smaller. And again, you might just instinctively think, hey, why not make more cars? And if they sell, then you make more money and you make more profit. Well, the more cars you sell, the less the demand might be there. The more cars you sell, maybe your factory is getting too tight. There's too many people in the factory. You don't have enough space. There are diminishing returns in productive qualities that tend to have a maximum output that you should produce to maximize your profit. There are a lot of different theories on how you can maximize profit in economics. We are not getting into that nitty-gritty. But one of the classic examples to maximize profit is to have the marginal revenue match, in other words, equal marginal cost. In other words, when the revenue you're bringing in is changing at exactly the same rate as the cost it is to produce them, that's when you can, that's one of the classic ways to maximize profit. Your marginal revenue matches your marginal cost. Believe it or not, this is extremely easy to prove, and it's one of the few proofs that we'll actually do. We know, let's go back to red. We know that our profit function is revenue minus cost. Or let me just drop the variable dependencies. P profit, that's a capital P, not lowercase p for price, which that kind of looked like a uppercase P there. That's annoying, but this was price. Okay, so this is profit is revenue minus cost. How do we go about maximizing something? We take its derivative and we set it equal to 0. So take the derivative. The derivative of profit is profit prime. This is a subtraction, so you can take those derivatives differently. So that's revenue prime minus cost prime. Then we set it equal to 0. So we get 0 equals R prime minus C prime. We can then add C prime to both sides and solve for R prime. And what we get is that C prime should be equal to R prime. C prime is marginal cost. R prime is marginal revenue. Easy. How do you maximize profit? You want to produce when your marginal revenue matches your marginal cost. With these revenue functions, historically speaking, you don't want to produce 0 items. Why would you want to produce 0 items? You're not going to profit off of that. And you don't want to produce the number of items that brings your curve back down to 0. So what's interesting is, with profit functions, the endpoints are almost unnecessary to test. I mean, I don't even want to say almost. They are unnecessary to test in our class. There are times when they're important to test if they don't give you bounds to begin with. Now again, this is if we don't give bounds. If I gave you bounds straight up, then you have to test the bounds. But if there are no bounds given for a profit problem like this, typically you can skip checking the endpoints because the endpoints are going to make 0 profit, and you obviously don't want 0 profit. So that's a fun little example. All right. Next up, example 3. Another word problem. Our favorite, right? A farmer has 1,000 feet of fence and wants to build, oops, we got a question. Yes, you are correct, example 4. I don't know why I said example 3. Even the piece of paper I have in front of me says example 4. All right, example 4, thank you. A farmer has 1,000 feet of fence and wants to build a rectangular enclosure along a straight wall. If the side of the wall needs no fence, find the dimensions that maximize the area of enclosure, as well as the maximum area. This is the classic horse pen or gardening problem, no matter how you want to look at it. And if you had pre-calculus, you should have seen one of these at least in there. But we handled it a little differently. Instead of handling it as a calculus problem with derivatives, we knew in pre-calc it was a quadratic function, so we knew that the vertex was always going to be the location of the max or the min, and the vertex has that formula negative b over 2a that you should still honestly remember. You can actually use calculus to prove that the maximum of a quadratic occurs at negative b over 2a. It might even be a homework problem. That's me whispering in case you didn't realize that. Okay. Picture's worth 1,000 words. So why do we have a side that doesn't need fencing? Maybe we're putting this along a barn or a house, or maybe there's just a wall that's already there. So the picture is going to look something like this. So here are the sides that need fence. So there's fence here, there's fence here, and there's fence here. Then we'll have our wall, and I'm going to draw it kind of wavy. It could be a river as well, assuming that it's perfectly straight. We're just going to say that this is our wall. It's already there. There's no way for us to make this garden or horse pen any longer than the wall. It's an infinite long wall in theory. So we have 1,000 feet of fencing, and we're not going to put fence along the wall because that's just a waste of materials. Because every inch or every foot of fence we use here is a foot we can't use over here, 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 and that's going to make the area shrink. And we want this area to be as big as possible so our horse has got plenty of room to roam, or we've got a ton of room for our garden. So this is a rectangle. Rectangles are easy. Rectangles have length and width. Let's call the side that only has one length of fence X, and let's call the vertical ones Y. Now, if that's Y, this has to be Y. They have to match. So X is the length parallel to the wall, Y is the length perpendicular to the wall. Do you have to do them this way? No. You can reverse the X's and the Y's. You can have two X's and then a single Y. Now, because this is a rectangle, it has a very obvious formula for area and perimeter. Area is length times the width, perimeter is just the sum of the sides. So the area of this would be the length times the width, which is just X times Y or Y times X. The order doesn't matter. The perimeter, which I'm going to put in quotes, because it's really just the perimeter of fence. We're not going to add up 4 sides, there's only 3. Now this problem can change. You can actually put in dividers as well, and then it's not a true perimeter, it's just the perimeter of fence. It's the sum of all the different fences. So we're adding up 3 sides. There's a Y plus an X plus a Y. Y plus Y is 2Y. So that's X plus 2Y. Again, Y plus Y is 2Y. So there's 2 different equations for this problem. When you deal with an optimization problem that has 2 equations with 2 variables, because this is kind of like a system of equations, we haven't done a lot of problems in here where there are X's and Y's. It's usually just X's, or any particular letter. In the next section we go to in 3.6, we're going to start dealing with multiple variables more consistently. We'll have X's and Y's littered all over the place and learn how to do their derivatives and such. But for now, we're just introducing the fact that we can have multiple variables, but we're not quite ready to do that extended concept yet. So what we need to do is focus on what we're actually trying to optimize. We want to maximize the area. This is the area formula, so we need to maximize this. This is the thing that we'll be taking a derivative of, ultimately. I want to type some notes down here below. We want to maximize the area function. However, we currently don't know how to take derivatives of multiple variables. So we need to eliminate one of them. Doesn't matter which. I much prefer to eliminate the y and only have this as a function of x because that's what we traditionally see. However, it doesn't matter, and that's why I've set it up this way, where we're actually going to solve for the y because it's easier. To do so, use the other equation, in this case, the length of fence, and solve it for 1, and plug into the area equation. Dot, dot, dot. We also know the number, the perimeter. It's 1,000. So instead of writing perimeter equals x plus 2y, I can write 1,000 is equal to x plus 2y. This is our fencing equation. the length of fence, the quote perimeter, because we know we have 1,000 feet of fence. Let's solve this for x because it's easier. You can certainly solve for y, it's just 2 steps instead of 1. All I got to do is subtract 2y on both sides, and you'll get 1,000 minus 2y is equal to x. This is important. This is a pivot point for us. This is a substitution method for systems of equations. If you're a little rusty with that, it's prereq material, Google, previous homework problems for review, etc., etc. So we're going to take this and we're going to plug it into the area equation. And there's another name for this. It's called the primary EQN equation. The primary equation is the one you want to maximize. The secondary equation is the one you have to use to plug into the primary. And this is a pretty common setup. So the area equation was A equals X times Y. So A equals X times Y, let me switch colors, is going to turn into A equals X, that got ugly, times 1,000 minus 2y. Wait, what am I doing wrong? I'm doing something wrong, aren't I? I have a bad habit. This says x equals, and I tried to plug it in for y. That was a goof on my part. X times y, this is x. So this right here is what goes there. So that's 1,000 minus 2y times y. Again, this was x times y, but the x is really 1,000 minus 2x. Excuse me, minus 2y. Blah. Like I said, I'm doing this in an uncomfortable way so that you're used to doing it either way, but you can tell how uncomfortable it is for me. I usually just instinctively always solve the secondary for y, so then everything's an x. But there's nothing wrong with doing it this way. I'm trying to keep us all on our toes. So this is the area equation. We now only have one variable. We can now do our calculus. We take its derivative. So we do A prime is equal to, well, that's a product. Let me pause on that. Let's distribute the y first. So area is 1,000y minus 2y squared. Now let's take its derivative. That way we don't have to use the product rule. We could have done it that way, but product rule is annoying when you don't have to. So that's going to be 1,000, because the derivative of 1,000y is 1,000, then minus, drop the 2 out front and multiply it, so you get a 4, decrease the exponent by 1. That's 1,000 minus 4y. That's our derivative of our area. That describes how the area is changing in relation to y, in relation to the length of the side of fence where there's 2 of them. Don't worry about overthinking that. Just go through our classic optimization. Set it equal to 0. So we go 0 equals 1,000 minus 4y. Solve this in any way you like. I'm going to add 4y to both sides. You could subtract 1,000 instead. So we get 4y equals 1,000, or you would get negative 1,000 equals negative 4y. You then divide both sides by 4. 1,000 divided by 4 is 250. So we get y is equal to 250. Y was the length of fence perpendicular to the wall. That was the fencing where we have 2 of them. Since this is the length of fence and we said we were in feet, this is 250 feet. And note there are 2 of these. So that's 500 feet of fence that we've used. We have got 250 feet on the left, 250 feet on the right. It should actually be ridiculously easy to figure out what this should be because we had 1,000 feet in total and we're using 500 of it currently. You just subtract 1,000 and 500. If you don't want to do any of that implicitly, just go back to this. length of fence, which was right here. X is equal to 1,000 minus 2y. We're going up here now. Going back to the equation that we substituted in. It's a pivot point because we're going to use it and we're going to come back to it. We know the value of y now. So we say 1,000 minus 2 times 250 is equal to x. 2 times 250 is 500. 1,000 minus 500 is 500. X was another type of length of fence, so it's 500 feet. And there's only one of these. So we got one side that's 250, this side that's parallel to the wall is 500, and then this side is 250 as well. Those are the dimensions that should maximize the area. Now, if you don't believe me, the area formula is quadratic. It's got a negative leading coefficient, so it's going to point down, and instinctively it has to be the maximum. You can actually prove this. Just by taking the second derivative. It's negative, concave down, and thus a max. If it was positive, it's concave up and thus a min. Well, a double prime, a prime was the 1,000 minus 4y. The derivative of 1,000 is 0. The derivative of negative 4y is negative 4. So it has to be a max because this is negative. It's negative everywhere. It's always negative. Whenever your primary function's quadratic, by the time you get to the second derivative, it's just going to be a constant. This can also be seen in the last example. If you didn't want to have to check the bounds since it was an unbounded problem, where is it? Here's our profit function. If you took its derivative, the derivative would be negative 140, which means it's concave down, which means it looks like this and has to be a max. There are lots of ways to prove that it's a max and not a min. And you are technically supposed to do that, but in the homework, you kind of get a pass on it a lot of the times. So what are the dimensions? DIM means dimensions. We want to build a 250 by 500 foot garden with two sides of 250s. It does matter. If you swap it, if you do this is 500 and this is 500, you can't even have this side because you've already used your 1,000 feet of fence. I think that makes sense. I hope that makes sense. It has to be 250, 250, and 500. If this had been 500, that makes this 500, and then you're just sandwiching the fences together on top of each other, and there's no area. But we also asked what was the maximum area because we want to know how much space our horses have or how much space our garden has. Especially with the garden, we got to go buy nutrients and stuff. We got to know how much to buy. Well, we had our area function, which is the x times the y. You could actually use the other version of it. You can use 1,000y minus 2y squared or 1,000 minus 2y times y. But this is the easiest version of it if you have x and y, so why not use it? So this is just 200. Let me write them in the right order. 500 times 250. God, that looks awful. Five times 25 is 125. Tack on the zeros. 1, 2, 3. And if you answered this 125,000 feet on a handwritten test, I would mark that wrong. Because it's not feet, it's feet squared, because that's 500 feet times 250 feet. Feet times feet is feet squared. All right. So let's do this again, but change it a little. Example 70. No, I'm kidding. Example 5. Same idea as before. 1,000 feet of fence. With a no fence wall. A non-fence needed wall with a no fence needed wall. But now we want a divider perpendicular to the wall. Find the dimensions, maximize the area as well as the area. So we still have 1,000 feet of fence, but now we want to have a section for our horses and a section for our garden. I know that sounds a little silly. Maybe we got a section for horses and a section for pigs. I don't know. Two animals that don't necessarily need to intermingle. So we want to keep them separate. So now, what our drawing looks like, we got our fence here, we got our fence here, we got our fence here. I'm just going to do F for fence, F for fence, F for fence. We got our wall along the top that we don't need fence. But now we want a vertical divider. And I didn't actually say where to place it. And in fact, the placement of it doesn't matter because it's not going to change the area. But I did mention that it needs to be perpendicular to the wall. So this is not what I'm doing. That would be parallel to the wall. We're doing this. Now it could be there, or it could be here, or it could be here. The actual location will not affect any of the math here. I can guarantee that. Let's split it in equal parts, but maybe you're dealing with horses and pigs and the horses need more room, so maybe you put it over here instead. I could put multiple enclosures. I could put one here and one here and one here, but we're just dealing with the one. So our area, the formula for this doesn't change, and let's stick with the same x's and y's. So we called the vertical one's y and the horizontal one x. So this is our x. And that's the whole distance across, not just the little slice. Then this is a y and this is a y. But we have this third length that is the same, so that's also a y. The area is still x times y. That's not changing. This length times this width, x times y. We're talking about the total area, so we don't have to do two separate areas. But now the fencing perimeter, we're not just adding the outer one, we also have to include the fence that's in here. So there's 3 of these y's and an x, so it's 3y plus x. The rest of the math is hardly going to be any different. We're going to need to take the perimeter one, which is 1,000 feet of fencing, 3y plus x. We're going to solve that for x. We're going to plug that into the area so that we only have one variable. We're going to take its derivative. We're going to set it equal to 0, and the rest is history. So for that 1,000 minus, I'm sorry, I don't want to jump the gun. The 1,000 equals 3y plus x. We'll subtract 3y on both sides to get 1,000 minus 3y is equal to x. This is our important equation that we'll use now and come back to. So we'll plug that into area. So our area, A, x times y is now 1,000 minus 3y times y. We substituted the x as 1,000 minus 3y. Let's distribute this, so we get A equals 1,000 y minus 3y squared. You can reorder if you want. Now we take the derivative. Let's use a notation I haven't in a while. Let's, instead of writing a prime, let's use dA over dy, because the derivative is taken with respect to y, not x. If these were x's, this would be an x, but they're y's, so this is a y. The derivative of 1,000y is 1,000, minus the derivative of 3y squared is 6y. Set it equal to 0. So we go 0 equals 1,000 minus 6y. Add 6y to both sides. You get 6y equals 1,000. Divide both sides by 6. And you get y is equal to 166.6 bar. And that's in feet. Now we plug this in to that substitution equation, to the secondary. We don't plug it into the x, we plug it into the y because this is a y value. So we're plugging into that little asterisk equation. So we say 1,000 minus 166.6 bar times 3. I'm supposed to write the 3 first, excuse me. That should be equal to the x. 3 times 166.6 bar is 500. That's 1,000 minus 500, which is, interestingly enough, still 500 feet. So our dimensions, it's going to be 166.6 bar feet by 500 feet. And there's 3 of these and 1 of these. So our area, the maximum area, will be the 166.6 bar times 500, which if you do that math, you're going to get 83,000, and then it's just a bunch of 3s. Feet squared. I want us to pay attention to these numbers. Let's look at the last problem. We made a 250 by a 500. And then the area that we got was 125 grand. This time, we make a 166.6 by 500. So that 250 has gone down significantly because we needed the extra bit of fencing. Basically, we took some of the fencing from the left wall and right wall and made the divider. So we pulled in the length of X's fence. We pulled it closer to the wall so that we could have the divider. And it brought the maximum area down from 125,000 to 83,000. That's a significant effect. We just lost like 42,000 square feet. But because we needed a divider, that's what we had to deal with. Now you might say, well, just go buy more fencing. Maybe you're out of money at this point. I don't know. So here's what's cool about this problem. If I threw in another divider, that just means there's a 4 here, which just changes this number, which just changes this number, and I bet you $1,000,000 that 500 is the same. Now, if I throw a parallel divider to the wall, that will change the ratio and proportion of numbers a little bit. But it's just fun how you can have kind of the same problem, but throw in more and more different little dividers and get different numbers. But again, it's really interesting that the length of the wall the length of fence parallel to the wall is not affected by dividers this way. I bet if you did a divider the other way, it probably wouldn't affect the other length, the y length. So that's a fun variation to that problem. And there's only one last thing I want to write. Let's just insert a new page to do that. There we go. Oh, perfect, that worked. So the primary and secondary thing I mentioned, let me just type it out. Secondary equations, let me say it a different way. The secondary equation is the one that gets substituted. The primary equation is the one that gets optimized. Now, both of the problems we did were maximizing, but you could minimize something as well if that's what was important. Minimize deaths of a virus, minimize losses of stock revenue, or stock profit, excuse me, not revenue. Both relative to things going on right now. All right. Hold on, I need a minute. Something's happening at my house. Give me about. All right, we're back. All right, so that's 3.4. 3.6, the final section of our test 2. Wait, is it 3.6? I think I have that wrong. I think it's 3.8. It is 3.8. I need to fix that typo then. 3.8. So going back to the material for this test, and I might have the wrong one in the homework, I will get that straight immediately after class, I promise. So it's 3.8 that we're going to cover. There we go, which is implicit differentiation. Now, if you actually look at the title of the textbook says implicit differentiation and logarithmic differentiation. We're not going to do the logarithmic part. As I've said, there's a lot of material we have to trim out of this textbook. Some of it is we'll come back to it and do it later. That's not one of them. So we are only going to cover the implicit differentiation side of 3.8. The reason I said 3.6 previously is because the last textbook we had, it was called 3.6. That's what it says on my little paper notes. So my bad on that. But implicit differentiation. Up to this point, we have been doing explicit differentiation. Differentiation. There we go. I don't mean explicit as in, explicit content. This is a CD you can't buy without parental units with you. Explicit means direct. Implicit means kind of indirect. Sometimes people say explicit is more obvious, implicit is more implied. There's a couple different ways you can interpret these words. So up until this point, we have been doing explicit differentiation. Let me not do a period, let me do a comma, which is used when there is only one independent variable. So just an x or just a y, etc. You can't have x's and y's. Now, in that last section, we started having formulas that we wanted to take derivatives of that had multiple variables, and we said, well, for now at least, we need to take one of those variables and put it in terms of the other. Well, now we're going to learn a way that we don't necessarily have to do that. For the optimization problems, it's still the best way to do things. This is going to be used for another setup that we'll see examples for, obviously. So when you have mixed variables, an x and a y, or an x and a z or anything, in an equation, implicit differentiation is a possible way to find an exact derivative. Implicit differentiation is based on the chain rule. Give you a second to get that. Okay. Chain rule states take ddx of both sides, sorry, not of both sides. Chain rule states that if you take ddx of a compound function, then the derivative is the derivative of the outside times the derivative of the inside. That's just a quick reminder of the chain rule. Even though you may not be able to solve for, say, y as a function of x, it can still be thought of that way. I.e., y could be considered a compound function. For example, the equation of a circle radius 5 is as follows. X squared plus y squared equals 25. This equation cannot be solved for y and expressed as a function of x because of the plus or minus square root property. If you solve this for y, if you try and solve this for y, you'll subtract x squared on both sides. I'm just going to show you really quickly. X squared plus y squared equals 25. Subtract x squared on both sides, you get y squared equals 25 minus x squared. Then you take the plus or minus square root of both sides to get y equals plus or minus square root of 25 minus x squared. But because of the plus or minus, this is not a function. So you can't write y as f of x. We can't say y is f of x because of that plus or minus. It's not possible to explicitly define y as a function of x, even though it kind of is. It's got this kind of thing going on, because sometimes it's positive, sometimes it's negative. It's actually both all the time. I'll say sometimes. Because this is the equation of a circle. It's a perfectly fine graph, but when you go to graph it, this is what it looks like. Here's your radius of 5. It fails the vertical line test miserably. Circles are not functions, so when you try and solve it for y, you can't do that because the plus or minus thing makes it not a function. We discussed that in pre-calc 1. So again, that's when this can be helpful. If I wanted to find the derivative of this thing, dy dx, you'd say, oh, well, first solve it for y and then take the derivative. But you can't solve this for y and take a derivative because it's not a functions, and you can only take derivatives traditionally of functions. So that's the explicit side of things. Now we're going implicit, and we do this kind of chain rule thing. So how does this work? What's the actual point of this? Basically, to apply the chain rule in this implicit differentiation method, take a derivative, good, of a variable, that is, and I'm going to underline this and caps it, not same letter, no more caps, as what you are differentiating with respect to need a dy over dx. In the term. Whatever letters are being used. It doesn't have to be y and x, it could be a and b, z and q, whatever. The variable on the bottom is what you're taking the derivative with respect to. The variable on the top is what you're trying to say the original function was. This right here is the derivative of the inside. So again, whenever you take a derivative of a variable that's not the same as the letters what you're differentiating with respect to. So this circle is the first one we're going to do. And I'm going to ask us to find dy dx, which means we're finding the derivative of y with respect to x. So when we're doing derivatives, we're treating the x as the regular input. But whenever we go to take a derivative of a y, we would have to throw this extra dy dx in. That's kind of like the derivative of the inside, because this y, yeah, it can arguably be solved for something, but we're not explicitly writing it. So there's an inside, so the dy dx counts as the derivative of the inside. Just saying the derivative of y squared is 2y would be the derivative of the outside. But we're not actually going to take the derivatives of the inside. We're ultimately going to solve for it. It feels a little weird at first. So again, all this said and done, the important part is right here. If you're taking a derivative with respect to x, anytime you see a y or a z or an a or a b, you're going to have to throw that dy dx in, or dA dx or dz dx. But whenever you take a derivative of an x term, everything is normal. Okay, example 1. A. And Do I need to write A? I don't need to write A, just example 1. If, let me just write the whole thing. If x squared plus y squared is equal to 25, this is the equation we're dealing with. Find dy dx. We're finding the slope of this function at any point. That's what we're doing. Dy dx is always slope. That's the interpretation. The rate of change of y with respect to x, that's y2 minus y1 over x2 minus x1 as we get super close to each other. If you do dx dy, that's not slope. That's the reciprocal of slope, in fact. So again, we're basically trying to find these slopes. So we're going to take the derivative of both sides. And whenever we don't match, why am I all the way back up here? Whenever they don't match, you do this extra chaining. So what do? We take d dx of both sides. That's going to be us taking our derivative. Anytime you're taking a derivative, that's the same thing we've been doing before. Take a derivative of both sides. So we go d dx of the x squared plus y squared equals d dx of the 25. And yeah, you probably don't need to put the 25 in parentheses, but I'm just being consistent. Again, when we went back in the last section, we were doing a prime, we were technically taking the derivative of both sides. It's just when you're solved for a variable, there's no real need to show the work, it feels like, because it automatically falls down to dA dx or whatever it might be. Okay, so I'm going to show the work in blue. For this x squared, we're saying, what's the derivative of x squared? Well, the derivative of x squared is 2x. These letters match, so this is normal. There's nothing new there. The derivative of x squared is 2x. No surprise. Plus. Now this letter and this letter do not match, so we need implicit differentiation for the second term. You need the implicit differentiation for the y squared. All right, so let's just imagine they did match. What would the derivative of y squared be? It would be 2y. Bring the 2 out front, decrease the exponent by 1. The fact that it's a different letter doesn't affect that part. That's the, quote, derivative of the outside. But because this letter does not match this letter, we have to chain it, because y, we're saying it's a function of x. Even though we're not solving for it, it could be, in theory, a function of x potentially. If it can't be, then you don't ever do it that way, and that's why we just imply it. So the derivative of the inside, y being a function of x, would be dy dx. Because y is the substitution variable in that instance that we're not seeing. It's back up here. Y is really this thing, so we're taking the derivative of that with respect to x. This is the inside. But again, it's not really a function, so we can't use it. So this is us pretending like we took that derivative. And then equals, the derivative of 25 is 0. The derivative of a constant is always 0. So again, the only new weird thing here is this part. And again, that's under the basically. Because this letter, I know I'm repeating myself a lot, but this is weird. Doesn't match this letter. We are chaining. We're considering the y as an implicit function, a function of x as well, even though we can't technically write it that way. So here was the derivative of the outside, the 2y. Here's the derivative of the inside, y equals blah, blah, blah. Well, dy dx. Again, we can't find it directly, so that's all we can do. Now we're supposed to be finding dy dx. Well, guess what? In the process that popped up naturally, there can actually be several of them. That's always possible, and we will see it. All we got to do from here is solve for dy dx. using our basic algebra skills. Let's subtract the 2x on both sides. I'll show the work since it has that weird thing, which will give us 2y times dy over dx equals negative 2x. Then we're going to divide both sides by the 2y. Remember, we're trying to solve for this thing right here. We just got to get rid of the 2y. When we would do that, let me go over here. The 2y's cancel. You get dy over dx on the left. On the right, the 2's cancel, and you get negative x over y. This is fascinating, even though the original thing is not a function, we can still take the derivative as if it were a function and get this relationship. Now, I'm not claiming that the derivative is a function. I'm not making that claim. I'm just saying that we can take a derivative of something that's not a function and actually get an answer. And this doesn't have to be a function. It's not explicit. It doesn't say y equals. It's definitely not a function of one variable. It's a function of two variables. Now, you might say, well, Mr. Beckner, if I know what y is, I could plug it in. But again, we can't say that y is anything because it's actually two things. This is the best you can do for this problem. There are problems that you could, in theory, plug the y in there and get a different looking answer, but that's the best we can do for now. For this problem, it's all we can do. Oh, I know, this was supposed to be a part A. Now I remember why. So everything we just did was part A. Part B coming up, we're actually going to go and talk about that slope stuff I was referencing. Find the slope of the tangent curve at the points 0, 5, 3, 4, and 5, 0. Now, two of these I could pull up the graph and know instantly. 0, 5, and 5, 0. Those are super easy to tell graphically. Let's just do that to the side. Here's our slightly weird looking circle. All of these are 5s and negative 5s on the ends. So the 3 points I have labeled are 0, 5, which is right here, 5, 0, which is right here. That's the first and the third. And then 3, 4, which is somewhere about here. Now at the 0, 5 at the top one, this is what the tangent line would have to look like. That slope is 0. So we should be able to prove that with the calculus. This point over here at 5, 0, that would be a horizontal tangent, that would be a vertical tangent line. And that slope would be undefined because vertical lines have an undefined slope. And then this one in the middle, you can't actually see the numerical value of it. Let me just draw that circle, just that single point. There's the point 3, 4. There's the tangent line. You can't tell the number, but it's at least negative. You can tell it's negative and not positive. So let's see if the calculus agrees with that. So again, we know dy over dx, which is the slope function, is negative x over y. We're just going to plug these 3 points independently. So for the first case, at 0, 5, dy dx would be negative 0 over 5. Just plugging in the x and the y values. That's the x, that's the y value, which is 0. And look at that. The slope at 0, 5 graphically said it should be 0. That's good. Let's do the 5, 0 next. The ones that are easy to tell. That says dy over dx is equal to negative x over y, which is negative 5 over 0, and anything divided by 0 is undefined. And look at that. That point, graphically, it says it's an undefined slope. And at the point 3, 4, some random value in between those two, our dy dx, our slope, would be negative x over y, so negative 3 over 4, and that's at least a negative, so that sounds good. I can't really judge the size of it. I would say that doesn't look like a super steep line. It looks like it's pretty close to 1 if I'm drawing that to scale, and that number is pretty close to 1, more specifically negative 1. The closer and closer you get to that 5, 0, though, this slope is going to go to like negative 10, negative a million, negative 10 trillion, until it goes undefined. So even though we cannot write a circle as y equals, we can still find the slope along the curve but using implicit differentiation. Even though we can't solve for y, in general, for the functions you're given 100% of the time, even though we weren't given this thing as solve for y, we're still able to solve for dy dx. And that's just because these terms tend to pop out 1 or 2 at a time. They don't end up being squared or cubed or to the 4th power, any funky business. So it's, in general, easy to solve these, at least for polynomials. So I love this circle problem. It's one of my favorites because it's easy to judge, it's easy to graph, it's easy to see the analytics to it. Once again, on the analytics side, what was the weird part? What's this implicit differentiation? We'll tell you how you have to take the derivative. You have to be told to find dy dx or dz dx or dx dy. You have to be told which to do. And then the bottom letter tells you when things get weird or not. When the bottom letter matches the thing you're taking the derivative of, it's normal. When they don't match, you have to throw in an extra term. And this dy dx, you could also just call that y prime. So instead of going 2x plus 2y dy dx equals 0, we could go 2x plus 2y times y prime equals 0, and then still subtract the 2x and divide by the 2y. Whoa, that was weird. I must have been scrolling when I was writing. So dot, 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 you end up with y prime equals negative x over y. The same thing. But some people will goof up when they have a y next to a y prime and try and turn that into a y squared. Oh, there's a 1 implied here. 1 plus 1 is 2. No, this is not a 1. That represents a derivative. So make sure you're using the notation that you're comfortable with. I don't care which notation you use. I just make sure, I only care that you are comfortable using it. So make sure you know which one you're comfortable with using. All right, enough ranting. Let's do another finally, and no part A or B this time, just example 2. So if, this one will be a little more involved, y to the 4th plus x to the 4th minus 2x squared y squared equals 9. Find dy dx, or y prime, however you want to write that. I think it's a better idea to use the dy dx's because then you can tell when the variable, the independent variable doesn't match the with respect to variable. So my preference is this one, at least initially for my students. I will admit, me on my own, I use prime notation because it's less writing, but I've done 1,000 of these, so I'm a little more careful. So what do? We take d dx of both sides. We take the derivative of both sides. How do I know to take d dx? Because this was an x, this is an x. If I said to find dx dy, I'd be taking d dy on both sides. So we go d dx of all that jazz, and then d dx of the 9 like so. Now, when the letters don't match, you throw in that extra dy dx into the term. That's the chain effect. That's the derivative of the inside. That's going to happen immediately. These letters don't match, so we'll need to chain this. So the regular derivative of y to the fourth will be 4y cubed. If this letter on the bottom was a y, this is all it would be, but they don't match, so we have to chain it. So we go times. And it's always the derivative of this thing, and then the dx is obviously the bottom. The bottom is always the same. That's going to be dx because that's dx. Because this was a y, that's why this is dy. If this letter had been a z, it'd be dz over dx. If this letter had been an a, it would be dA over dx. If the letter on the bottom was a q, it would be dy over dq. Derivative of the outside times derivative of the inside, plus x to the fourth, that matches our with respect to variable, so that's just 4x cubed. No funny business there. Now here's where things get interesting. X squared times y squared is a product rule. That's a product. So we got to remember derivative first times second plus second times derivative. I think I said that wrong. First times derivative of the second plus second times derivative of the first, or whatever variation you like. Now that -2 is going to get annoying to have to deal with along the way, so I'm going to go -2 and then open a parentheses, and then inside of this parentheses will be the product rule. This x squared y squared is a product. That's why we have to treat it so. And not only is it a product, it's a product of different variables, so one of them is going to get this implicit style differentiation. But I'm leaving the -2 in front of everything. Now, I like to go I like to go second times derivative of the first, excuse me. But I'm just going to write them in the opposite order. So the first times the derivative of the second. So the first is the x squared. The derivative of the second, the derivative of y squared. Sorry, I got lost in translation for a second. So the x squared, I use the first, which means I'm going to use the derivative of the y squared. The derivative of y squared is 2y, but those letters don't match, y, x, so we need the additional dy over dx. Again, I took the first times the derivative of the second. So the first was the x squared, the second is the y squared. The derivative of the first is 2x. The derivative of the second is 2y dy dx because of the lack of matching variables with the with respect to part. So that was the first times the derivative of the second, then plus, we're going to do the derivative of the first times the second. The derivative of the first is 2x, no implicit needed, times the second is the y squared. See, the dy dx only pops up in one of those in the product rule because only one of those products didn't have a matching variable. So again, this was plus the derivative of the first times the second. That's the order I did. Equals, don't forget the right-hand side, equals the derivative of 9 is 0. Now what we need to do is ultimately solve for dy dx. First, let's distribute the -2 that's here. So we'll get 4y cubed dy dx plus 4x cubed minus, now there's already 2's in each of these, so that's going to be a -4 x squared y dy over dx, and no, these x's don't cancel, -4 xy squared equals 0. Now, the first problem we did, example 1, when we did that implicit derivative, there was only a single dy dx, so it was very easy to solve for. If you can't do that algebra, I'm terrified. I really am. I'm not trying to be mean. This is much more complicated, but in pre-calculus, you were taught these methods. The dy dx is here, and it's here. Now, if these were combinable, we could just say 4 plus 6 is 10, but they're not, because that's a 4y cubed in front of it, a minus 4x squared y in front of it. So they're not combinable. So instead, we have to take that alternative approach, which was to, come on, let me type just a little lower. Don't make me go to the next page. I'll write it. I'll write it. Move all terms with dy dx to one side, all others to the other side. Anything that has the dy dx, or y prime if you prefer, needs to stay on one side, everything else goes on the other. Now, I don't actually have to move any of the dy dx's because they're all on the same side. That doesn't have to be the case. They're both on the left. So the things that we need to move, this 4x cubed doesn't have it, and this minus 4x y squared doesn't have it. So they've got to move. To move the 4x cubed, you'll subtract. To move the minus 4x y squared, you will add. So what we get is 4y cubed times dy dx minus 4x squared y dy dx equals, and I'll show the ones that I moved in red. So again, they just change signs. The 4x cubed becomes negative 4x cubed because of subtraction. This minus becomes a plus, 4xy squared. You could have written the positive term first, it doesn't matter. Now what we're going to do is factor the GCF of dy dx out. Everything on the left has the dy dx, which means it's a common factor. That was weird. Why'd it go away? So we can factor that out as a GCF. So we go dy dx, open parentheses. We're left with 4y cubed from the first one minus 4x squared y from the second one. And that will be equal to, I'm going to go ahead and swap the order of those just to get the positive term first. 4xy squared minus 4x cubed. And then we just divide by the thing next to the dy dx, divide by the parentheses. I'll show that step. Divide both sides by 4y cubed minus 4x squared y. Giving us our final answer, maybe, of dy over dx equals 4x y squared minus 4x cubed over 4y cubed minus 4x squared y. Now, what some people will think is that this is the answer. The answer, excuse me. But it's not, because this is simplifiable. And it's not out of your realm of what you should know how to simplify. When you've got big crazy fractions, if they've all got something in common, you can take it out. Well, there's GCFs in the top and the bottom, so that might be helpful. Let's do GCFs first. So we get dy dx. How are we on time? Okay. dy over dx, ooh, that was weird, equals, there's a GCF of 4x in the top, open a parentheses, you'll be left with y squared from the first term, minus, and then just a single, excuse me, then an x squared from the second one, not a single one. In the bottom, there's a GCF of 4y. And when you factor that out, when you take 4 and y from the first term, you'll still have 2 of those y's left over, so that's a y squared minus. When you take the 4 and the y from this one, you still have the x squared. And what's unbelievable is that those two parentheses match, so they can cancel, and we get dy over dx. Again, this and this will cancel. Also, the 4's cancel. Everything goes away except the x and the y. So the slope formula, the slope function for this crazy original function we had all the way back here, y to the fourth plus x to the fourth minus 2x squared y squared equals 9. The derivative of this thing with respect to x, in other words, its slope function, is just x over y. How in the heck did that happen to be so simple? Does it always turn out to be that simple? No. But this one was very simple for one particular reason, and I want to show you why. This is fun. Notice the similarity of the slope to this in comparison to the slope of the previous one. It's negative x over y versus positive x over y. Let me show you why that is. So just kind of a observation. Start with a circle, radius 3, which that would be x squared plus y squared equals 9. It's always x squared plus y squared equals the radius squared. I'm sorry, not a radius of 3, a radius of square root of 3. So if the radius is the square root of 3, the right side is the square root of 3 squared, which is 3. Now let's just square both sides of this. So you get x squared plus y squared squared equals 3 squared. Well, that's x squared plus y squared times x squared plus y squared equals 9. And then FOIL this out. We're just having fun here. This is not something I'm gonna ever ask you to do homework or test. This is just us having fun for a minute. If you FOIL this out, you'll get x squared, I'm sorry, x to the fourth. X squared times x squared is x to the fourth. That's the first. The outer would be a plus x squared times y squared. The inner would be the same thing, x squared y squared. And the last would be a plus y to the fourth, and then that's equal to a 9. Combine like terms, the middle, that's like a plus a, so 2a, but it's x to the fourth plus 2x squared y squared plus y to the fourth equals 9. Look at how similar this is to the original function, not the original function, the original equation I gave you. It's just a minus here instead of a plus. What that says is this is actually really similar to just having an equation of a circle and squaring both sides. There's a very strong correlation there. And the derivative of the circle was negative x over y. It's just squaring two sides of an equation doesn't do anything to the actual equation. Just squaring both sides. Remember, whatever you do to one side of an equation, as long as you do to the other, you're not changing anything. So this thing should have the same slope as before I squared it. Again, because that was just an algebraic manipulation. So the slope of this thing should be the slope of this thing. And it's this middle term being positive instead of negative that is what causes the sign change. You could also argue that the squaring could have that effect, but it's really this term. So we just took an equation of a circle, squared both sides, and we got basically the same thing. So this is basically 1s, just a circle. It's just a circle that's been squared on both sides. If you graph x to the fourth plus 2x squared y squared plus y to the fourth equals 9, it would be a circle with a radius of square root of 3. That is why, after all the algebra was said and done, this derivative mirrored it so well. But again, it was that one teeny little sign change. If I put a plus there, then this would have been a negative instead. That's the only effect that it would have had. If I had made this a plus originally, then this derivative would have been a negative and it would have correlated 100%. But I wanted just to do a subtle difference there. Literally. Pun intended. All right. I thought I had another one, but I'm not seeing, my papers got shuffled for reasons. Yeah, I'm not seeing my third example. Let's make up one. Insert page. There we go. That I tell you, this program, it does some weird, wacky things sometimes. I know occasionally it's my fault, but it's unpredictable often. Let's do e to the 2y. So we're gonna say if e to the 2y plus x is equal to the ln of y, find dy dx. So we're going to take the derivative of both sides. We're going to take dy, oh, yeah, this is about to crash. That I was right, this thing was being wacky. Give me enough time to finish. Please. And the annoying thing is if this crashes, I'm gonna have to reload, that might not even be there. Come on, all right. All right, let's try Control-Delete. Isn't technology fun? Oh, there it was just fixing itself. Timing! Sorry, that's I don't know why I just said an inside joke. That was silly of me. Was it this one? Nope. There we go. How much did it save? How much did it save? Holy cow. It saved most of it. All right, insert new page. Example 3. If, what did I say? I was going to do e to the 2y plus x equals ln y. I think that's what I came up with. Find dy dx, aka y prime. So we take d dx at both sides, and it thought I'm on orange still. So d dx of the left, d dx of the right. E to the 2y plus x on the left, ln of y on the right. Oh, look, derivatives of exponentials and logarithms. You got to remember those formulas. They don't ever go away. So the derivative of e to the 2y, remember, the derivative of an exponential is the exponential times the derivative of the inside. So that's going to be e to the 2y, that's the exponential itself, times the derivative of the exponent itself. The derivative of 2y would normally just be a 2, but because these letters don't match, you have to throw in that dy dx. So again, the derivative, the original exponential times the derivative of the exponent, but the derivative of the exponent, this letter did not match that letter, which is why there's a dy dx. Plus the derivative of x, these letters do match, so just take a normal old derivative, which is 1, equals. These don't match, so you'll need a dy dx times whatever it is. Let's go ahead and put that there. What's the derivative of the natural log of y? It's 1 over y. Again, that's a formula you're supposed to know for this test. Both of those. It's just been a couple classes since we used them. Well, we got dy dx's on both sides. We can solve for them. And I'm going to have to go there a little quick since this thing froze and ate my time. So let's collect. Let's first reorder this just a little prettier. So that's 2 e to the 2y times y prime, or dy over dx, plus 1, equals 1 over y times dy over dx. Let's move the dy dx's left. That's my choice. If you want to move them right, you can. So I'm going to move this term to the, actually, I'm going to take that back. I usually move the dy dx's to the left, but I'm not going to this time because the only non-dy dx term is here on the left, so it's going to be easier for us just to move this term to the right. I know it looks like a Madden drawing now. So we're going to move this term. I'll show that because I'm going back on what I said. 2e to the 2y, we're going to subtract that on both sides. So that's going to give us 1 equals 1 over y dy over dx minus 2e to the 2y dy over dx. Take our GCF out. So we get 1 equals dy over dx, parentheses. 1 over y is what we're left from the first term, minus 2e to the 2y is what we're left with from the second term. And then we just divide by the parentheses. So we're going to divide the 1 by that parentheses. We're going to divide by the dy dx by the parentheses. What we get is 1 over y minus 2e to the 2y is equal to dy dx. This is not in an okay format for the answer because it's a compound fraction. The easiest way to simplify these, the only denominator inside of the fraction is a 1, so you multiply all tops by the LCD, which is y. Because this is a y and it's the only denominator, you're going to multiply the 1, and this thing by a y. Why is that doing that to me? Stop it. So I will show that in color. We're multiplying the top one by a y, this one by a y, and this thing by a y. And that's still equal to our dy over dx. The reason we do that is so these y's cancel right here. We want those to go away so there is no more compound fraction. So what we get for our final answer in the top is just a y over. The bottom left is now just a 1 minus, let's put that y up next to the 2 and e to the 2y. That got really sloppy. dy over dx. There is our slope formula. That one's a little more intense algebraically because of the compound fraction part. It's also a little more intense calculus-wise because you have to remember all your derivative rules that your teacher told you had to remember all of. But if you put all that together along with the algebra we did in that last example, it's not too terrible. So again, we had an equation that you cannot explicitly solve for y. Even the best mathematicians analytically cannot solve this for y because one of the y's is up in an exponential and the other's in a logarithm. That is insane. But even though we can't explicitly solve this for y, even if it is a function, even if it's a function that we can't solve for y, we can still find its derivative. It just happens to be that the derivative has some y's and x's in it potentially. It's interesting, it doesn't even have any x's. The derivative is entirely dependent on the y value, not on the x value at all. So if you graph this thing, the left and right position doesn't even affect the slope. It's only affected by the vertical position. It's kind of fascinating. That, I believe, should be the end of 3.8. All right, daily notes. Scroll down, just ignore that stuff. Yeah, we're good. So we finished 3.8, so that should also be due on 7/2, a week from today. So our test date, we can concretely say, how does July 3rd through 6th sound? Since it's over a weekend, I'll give you 4 days. I'll give you a Friday and a Monday combo plus the in-between. So the test dates will be Friday, July 3rd through Monday, July 6th. That's still 3 full days because there's a holiday in there, so that's 3 full regular days. I know one of them's a weekend day, but that's not the end of the world. I know a lot of us are going to be doing it on Monday anyways, so we can study. But that's a pretty good range. And it will flow just like the last one. It'll be 2 hours. The number of questions is to be determined. I will have a review made for you by Tuesday afternoon. If I can get it in sooner, I will get it in sooner, but I'm not going to promise any earlier before Tuesday, 5 p.m. You got your homework due dates. I'll make sure everything is correct in my math lab as soon as I hit the end meeting button. If you don't have any questions, have a great weekend. Email me if you do have any questions. Keep working on the homework, keep those grades up, study hard, and we'll see you on Tuesday. Take it easy, everyone.